Okay. So Hawc is located here in Mexico at Sierra Negra, that is in Puebla, and it was constructed at an altitude of 4,000 meters above sea level, and it has a geometrical area that is about 20,000 square meters. And the thing about the selection of the site is because we were interested in some energy range in which the air showers get its maximum just at this height. And well, it was constructed with 300 water cherry cup detectors, and later it was implemented with 345 outrigger detectors. Well, these outrigger detectors are still being uh, being characterized, and we are just still working only with the 300 Warenkorb Cherenkov detectors. And well, the Warenkorb Cherenkov detectors have this specification. They have a diameter of 7.3 meters, a height of 4.8 meters, and each of it is filled with 200,000 liters of purified water. And at the bottom, we have these four PMTs, so we can recollect the Cherenkov light that is generated by the secondary particles from our air shower. And well, with this, what do we have? We are capable to have a gamma hadron separation or identification in this case. And here I'm showing you two different kind of events, one generated by a photon and one generated by a proton. And what we have is that uh, the 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 time that we have of these events that coming are really smooth around the core that we can reconstruct. While when we are checking about the proton, we have that this distribution is not that as smooth and is characterized by these hotspots that are mainly muons that come and deposit a big amount of charge at these detectors. And well, by using this, well, we just check on the arrival times from the shower, and also we check for all the charge that is deposited in each of the PMTs. And with this, we can have an image of the shower, of the lateral distribution of the shower, and we focus on which events have high charge deposited around 4 meters from the core. And this is one of the ways that we can check if it was an event generated by a proton or generated by a photon. And also we have now implemented an energy estimation method. So currently we're working with 11 energy beams, and each of these beams, well, we are mainly using from beam B to beam L. We are still working in better algorithms to understand better this low energy regime. And also, we have two different methods that we can use to estimate the energy. One depends purely on the charge deposited in the PMTs from a certain distance from the core, and this is called the ground parameter method. And the other one is by using artificial intelligence algorithms. In this case, we're using neural networks. And well, both of the methods are really consistent. And well, it only depends on what do you want to analyze for deciding which one of these methods you can use. But both methods are consistent within each other. And well, I think that is the only thing that I wanted to talk about the Hawc detector. And now I'm going to focus on the recent results from this Hawc experiment. And the first thing that I'm going to talk about is the cosmic ray spectrum. So for the cosmic ray spectrum, uh, we have made this analysis of the all particle cosmic ray spectrum. And well, this was in 2017. And what we have is that we simulated all, all of the part of the cosmic rays from light from heavy flavors. And well, what we have here, the Hawc data points are this one in blue. And we see that they are in agreement with the cosmic ray spectrum from other experiments, just as Attic and Graves and and other of those. Well, and here we put as a reference the light particle spectrum measured by CREAM. And well, one of the highlights of this result is that we seems to have a spectral break around 50 TeVs. And well, we just needed to check whether this break is statistical significant. And well, that was made just a few years later. Well, in fact, the bad result that I told you about was only taken around 250 days of data. And this one is with 4 years of data. So, well, what we did is check only for the light component of the cosmic rays, specifically only protons and helium. And we check the spectrum in this energy range. And what we see is that, in fact, we are still seeing this spectral break. And well, it was shifted just a little bit. Before it was around 50 TVs, but now what we have is that it is around 10, 20 TVs. And it was previously reported, and it was now confirmed by, with all other larger ES data sets that we have taken, and also with improved simulations. And well, this break is, as I told you before, near 24 TVs. And what we see is just a softening of the spectrum, and the decrease goes really smooth. It goes from this spectral index of 2.51 to 2.83. So this is one of these recent results. And when we compare it with other experiments for the light component of the cosmic rays, we see that it is really in agreement with the other experiments, precisely with Attic, CREAM, and Nucleon. And also, Dampte has a result that is in agreement with this softening of the spectrum at around 10 TeVs. So, well, now about the anisotropies of the cosmic rays. What we have is this previous work of 2018, where we check the anisotropies at large scales and small scales at different energies. So, well, as we see at high energies, these anisotropies just start disappearing. And when we check for the small scale anisotropies, we get these little hotspots. So these hotspots has been, in fact, observed by other experiments. In fact, Milagro, I think, was one of the first that checked these regions. Well, and well, we have the region A, that is the most prominent of all of these regions. Region B is also is not that significant, and region C. But the improvement in this analysis is that we get new insight of this other region that wasn't detected previously. And well, it's weaker than the others, but well, it was just discovered with this work. And well, the other work that has been made about the anisotropy of cosmic rays was made using Hawc data and Ice Cube data. And well, we did this collaboration and focus only on events that have a median energy of 10 TVs. And well, uh, when we make the merge of all the data, we have that the full sky observation just get rid of the degeneracy between the spherical harmonicals components. And well, when we check at small scales, well, we see also all these regions. And well, in fact, at large scales, you can see here the local interstellar magnetic field line is here depicted at the with this black line, black solid line. And as you can see, well, the deficit and well, the excess that we see are kind of perfectly separated by this line. And well, still we need to check what is one of the causes of these excesses that we are seeing at small scales. So this is work that we're still dealing with. And well, the last topic that I want to talk to you about the recent Hawk results is about the cosmic ray accelerators. So as I said it before, we are concerned or really interested in try to identify these cosmic ray accelerators in the galaxy and also of extragalactic origin. But here I'm only focusing on those from galactic origin. And well, this result was published in 2020, and it was just after we make one of our catalogs. I think it was the third catalog, and we detected several sources that have an energy above 50, 60 Bs, and also some other sources have significance above 150 TVs. Well, I'm talking here about gamma ray emission. So, well, if we have sources here in our galaxy that can reach these high energies, such as to well, a few hundred TVs, we have several hypotheses of what is the cause of this particle acceleration that maybe produce these gamma rays. And well, we have two models. Well, in fact, there are three. Or well, the leptonic model, where we have electron positrons that are being accelerated in diffusive shocks, or hadronic models, where we have also well, mainly protons that are being accelerated at relativistic energies and are able to produce gamma rays via pion decays. And the other scenario that we can imagine is just a merge of those of these two, a leptodronic scenario. And well, from all of the sources that we detected at these high energies, we start to make of an analysis on those sources that can have this high energy and maybe possible cosmic ray accelerators. So the first one is this source, J2227 plus 6010. And well, this source is in a really rich populated region. We have I'm not quite sure how many pulsars, but I think there are two pulsars and also one supernova remnant in this region. So, well, in fact, for the leptonic scenario, it is assumed that this electron positron acceleration mainly occur on the pulsar wind nebula or by pulsars. And for the hadronic scenario, we believe that it is mainly the gamma ray emission is mainly generated at the supernova remnant by diffuse acceleration in shocks. So we need to try to identify which one of these scenarios is the one that can explain the emission of these high energy TeV photons. And well, sorry. And well, concerning this region, well, we checked whether it was generated this emission by the pulsars here in this region or by the supernova remnant. And what we have is that the more favorable scenario is that one that is assumed by is by assuming that the high energy gamma ray emission is generated by protons in the supernova remnant that is known as G 106.3 plus 2.5 to 2.7. And well, also we can interpret this emission from both hadronic and leptonic emissions. And one thing that we need to just discard any of these scenarios is just to make multi-messenger analysis. In fact, what we really need is that if we have hadronic emission, we need to have correlation with neutrinos. So, well, we need more results from these neutron experiments like IceCube, but well, just by checking the spectrum, we can see that the spectrum reaches hundred of TVs, and when we assume an hadronic scenario, we get that the proton spectrum must have a cutoff energy above 800 TVs. So this means that this source could be a galactic pevatron. So we are still working on this interpretation, and uh, and well, uh, as I said, we need to check if this scenario is possible. And well, this is something that I'm going to tell you later. And well, for the other source that we have is the source that is called Hawc J1825-134. And also, as you can see, most of the sources that we have at high energies are in rich populated zones. So here we have three sources that have been detected, but one of these sources extends its spectrum up to 100 of TVs. So from this, we check in this region what else is around. And well, what we have is that there's a lot of sources again. There are many pulsars. And one thing that we have here is that we have a region that is associated with a giant molecular cloud. So we check whether the leptonic or hadronic model was favored. And what we have is that the favored scenario was PV cosmic ray protons colliding with the ambient gas. And this ambient gas, here I'm showing you the columnar density of this gas, and is associated with a young cluster, a young star cluster. So, well, we identify that it is possible that this cluster may be another pevatron. And well, the other source that is really interesting of the recent results from Hawk is the region of the Cygnus cocoon. And well, this region is characterized by a massive star formation rate in a bubble region. So we also have a lot of sources here. So we get rid of all of the hotspots, well, of the sources that are contributed here. And after getting rid of this signal, we are still getting an excess. And we name this excess as, well, this source, J2030 plus 49. And, well, we check for the spectrum of this region, and well, it reaches high energies also. It extended above well, 100 TVs, and we check if the emission may be generated here in the bubble, more specifically in this star formation zone, where we have, in general, OB stars. And well, the OB stars are characterized by high winds that may be the the possible explanation for a region of of gas that where we have these interactions. And well, the one of the last studies that we have made from the possible cosmic ray accelerators is of the one concerning this Hawc source. And well, we check for all the possible scenarios, as I told you, the leptonic, hadronic, and also leptodronic scenario. And well, the possible origin for this source is, again, there are a lot of other sources that may be correlated with this emission. And we have a pulsar there and a supernova remnant also. So the thing with this source is that both of these scenarios are really plausible. So we need more data, more joint analysis with other experiments, so that we can get an idea if this gamma ray excess is really due to a leptonic scenario or an hadronic scenario. And well, there are many other works about cosmic rays in the Hawk collaboration. I think I'm do not have the time to talk about all of these works, so I'm just uh, put you this in this slide so you can access all of these works. And well, one that I want to mention that I think is quite interesting is this one, the characterization of the Hunga pressure wave with cosmic rays by Hawk. I don't know if you know about this Hunga volcan, but it was just a huge eruption that generated a shockwave that propagated all around the world, and well, we were able to characterize this by using cosmic ray data. And well, just um, just a summary. Well, we have many cosmic ray studies that has been performed by using the Hawk Observatory, even though Hawk was think to be a gamma ray observatory, but well, most of the events that we have are mainly cosmic rays, so why not use that data? And we are still working on analysis techniques so that we can improve our gamma hadron separation and also our energy estimation. And well, the thing that I want to highlight here is that we have detected potential cosmic ray accelerators, and uh, these are the mainly sources that we believe are the cause of this high energy gamma ray. We have supernova remnants, bubbles that are characterized by a massive star formation rate, and also star clusters. But these star clusters need to be, well, rich of OB stars. And we have several other analyses in development and others under collaboration review. And we are making an upgrade on the cosmic ray spectrum and extending up to 10 to the 15 EVs. So, and we also are checking the composition of the cosmic ray spectrum not only for hydrogen and helium, but also by implementing the heavy component of the cosmic rays. And this analysis is in progress. And also we are checking for an update on the cosmic ray anisotropy so we can set more about. And we are also improving it with 8 years of data. And well, I think this is one of the most interesting. In fact, I think it's just on the last review from the collaboration, and is that we are testing the molecular cloud paradigm for one of the sources that I mentioned you. And this is by assuming that the protons are being accelerated in this supernova remnant. And I think in a few months, maybe it's going to be just published. So thank you.
Thank you very much, David. First question.
Very nice and comprehensive review. You had mentioned that these outriggers have now been installed, right? 375?
They're installed, but we are still working on how to analyze that data.
Okay, but they are working. They are on site.
Yeah.
So apart from improving the gamma to hadron separation, which of course it will probably help, are you also planning to use it for more precise study of cosmic ray composition? Because now you will have huge amount of information on muons, right, from these outriggers. If I just scale up the number, it's like 25,000 square meter of muon detection. So that will give you a very high sensitivity for elemental composition.
Yeah, we're hoping for, but we're still working on that. Yeah, but in fact, one of the other things that are helping us with the triggers is that we can have more high energy air showers. So yeah.
But the nice part is that you will overlap with direct experiments like AMS, which have measurements up to, few tens of TeV, and then you can really tune your Monte Carlo.
Yeah.
So that will be a great combination.
Yeah, we're looking forward.
Thank you. Are there more questions?
Just one comment about this Tonga volcano. In fact, in GREAT, we have also observed and we compared your results.
Nice.
So there is going to be an invited talk after lunch. I'm sure it will be there. So yeah.
Nice.
Thank you.
No, thank you.
Just a minor question. In your previous to last conclusion, you speak about ultra high energy cosmic ray. I guess you mean pevatrons, right?
Yeah.
No, not ultra high energy. And the main factor, obviously, which stops you going up is the purity of your selection, right? Discrimination of protons.
Yeah.
With gamma.
Yeah.
Yeah. Thanks a lot. So from my side, I would be interested to understand. So you early showed cosmic ray breaks, and you said that you had a break at 50 TeV, and then it moved to lower energy. But my understanding was one break was the all particle spectrum, and the other break was
only
proton and helium. So there's no contradiction, right?
No.
Because so the break at 50 TeV is not ruled out in the sense of being a break in the all particle spectrum, is it? Or
yeah.
So you have not changed that. It's only that
No.
you are more specific now by going to the light component and seeing the break of the light component at lower energy.
Yeah, exactly. That's the only thing.
Yeah.
But it's consistent.
Which makes a lot of sense. Yeah. Okay. Thanks a lot.
Yeah, just about the same point with the needs which you see in the all particle and proton helium component. If you look at the indices which you extract from that, I think if I compare that to data from Cascade, I think also the indices actually agree, right?
Yeah.
I just compared it to the published data. So it gives a very consistent picture. Of course, we don't know what the sources are for these different needs, but I mean, at least the data seem to be consistent with one another.
Really consistent within each other. Yeah.